Somewhere in our galaxy tonight, there is an object about the width of a city. Driving where possible, which it is not. It contains more material than our entire sun. Take a single teaspoon of it. Not a bucket, not a barrel. A teaspoon. That small quantity would weigh about 1 billion tons. It would weigh roughly as much as a mountain. If you could somehow bring it here and set it on the ground, it would not sit there. It would fall straight through the crust of the earth, gathering speed, and it would not stop until it reached the center. This object is spinning, not slowly. Some of them turn hundreds of times every second, faster than the blades of a kitchen blender, with a surface moving at a substantial fraction of the speed of light. Some carry magnetic fields a quadrillion times stronger than the one that guides a compass needle, strong enough to distort the shape of atoms. And it has a surface. That is the strange part. Black holes have no surface, only a boundary. This has actual ground, solid, crystalline, unimaginably smooth ground, with mountains on it that are measured in millimeters. It is the leftover heart of a star that died, and there may be 1 billion of them scattered through the Milky Way. Tonight, we go and stand on one, carefully. If you find calm in the extreme and beautiful physics of the universe, consider subscribing to the channel. Let these strange, distant objects carry your mind somewhere restful as we drift together through the dark. Welcome aboard, astronaut. Tonight, we drift through the cosmos. We travel out along one of the spiral arms of our galaxy, past clouds of glowing hydrogen where new stars are being assembled, past clusters of hot blue giants burning through their fuel at a reckless pace. And we stop beside one of them, a star perhaps 20 times the mass of our sun. It is enormous, brilliant, and it is about to run out of time. What happens next takes less than 1 second, and it will produce something that should not be possible. Tonight, we will watch that collapse happen in slow motion. We will find out what stops it and why the answer required a completely new idea about matter. We will measure the density, the gravity, the spin, and the magnetism, and every number will sound like an exaggeration until we work through where it comes from. Then we will go inside, through the atmosphere, which is a centimeter thick, through a crust made of crystallized iron, down into a layer where matter arranges itself into shapes that physicists have named after pasta, and which may be the strongest substance in the universe, and finally, into a core that nobody understands. We will end by watching 2 of them collide, and by finding out where the gold in your jewelry actually came from. Settle in. Let your breathing slow. Nothing tonight is in a hurry, except the star. Let us begin at the end of a massive star's life. Stars survive by balance. Fusion in the core pushes outward, gravity pulls inward, and for millions of years, the two hold each other in check. A massive star runs through that fuel quickly. It fuses hydrogen into helium, then helium into carbon, then carbon into neon, oxygen, and silicon. Each stage releases less energy than the one before, and each burns faster. Hydrogen might last 10 million years. Helium, 1 million. Carbon, 1,000. Oxygen, about a year. Silicon burns for a single day. Silicon fusion produces iron, and iron is where everything stops. Fusing iron does not release energy. It absorbs it. For the first time in the star's life, adding fuel to the fire puts the fire out. So an iron core accumulates at the center, growing heavier as the shells above keep burning. It is supported not by heat, but by the pressure of electrons crushed tightly together, resisting further compression purely because quantum mechanics forbids them from occupying the same state. That support has a limit. When the iron core exceeds about 1.4 times the mass of our Sun, the electrons can no longer hold. At that moment, the star has been alive for 10 million years. It has 1 second left. Now, let's go deeper into that second. The collapse is astonishingly violent. The iron core, roughly the size of Earth, falls inward at up to a quarter of the speed of light. In a fraction of a second, it shrinks from thousands of kilometers across to about 20. As it compresses, something remarkable happens to the matter itself. The pressure becomes so extreme that electrons are forced into atomic nuclei, where they combine with protons. Each merger produces a neutron and releases a neutrino. An entire stellar core converts in an instant into neutrons. That conversion removes the electrons that were holding everything up, so the collapse accelerates further, and it produces a flood of neutrinos so vast that it carries away about 99% of the total energy of the event. Ordinarily, neutrinos pass through everything unnoticed. Here, briefly, the material is so dense that even neutrinos are trapped. Then the core reaches a density comparable to an atomic nucleus, and it stiffens abruptly. The infalling material slams into that incompressible center and bounces. A shock wave races outward, stalls against the weight of the star still falling in, and is then revived by the enormous pressure of escaping neutrinos. Over the next hours, that shock blows the entire outer star apart. We see it as a supernova, a single star briefly outshining an entire galaxy of billions. But the explosion is not the point. It is the packaging. Left behind at the center, a sphere of neutrons about the size of a city, spinning, glowing, and containing more mass than the Sun. But that's not all, because one of these events was written down. In the summer of 1054, astronomers in China recorded the appearance of what they called a guest star. It appeared in the constellation we now call Taurus, and it was extraordinarily bright. Their records are precise. It was visible in broad daylight for 23 days. At night, it remained clearly visible for close to 2 years, before finally fading from sight. Observers in Japan noted it as well, and there are probable references in other records around the world. 9 centuries later, telescopes revealed what sits at that position. An expanding cloud of glowing gas and filaments, roughly 11 light-years across, still visibly growing outward. Measure its expansion rate, work backward, and the arrival date matches the historical accounts almost exactly. Then, in 1968, astronomers found something at the center of that cloud, a pulsing radio source flashing 30 times per second. It was the collapsed core, still there, still spinning, 970 years after somebody in China looked up and wrote down what they saw. That connection is remarkable. A note made by an observer with no telescope, no physics, and no concept of what a star even was, turned out to be the birth certificate of an object we can now measure to extraordinary precision. There are estimated to be between 100 million and 1 billion neutron stars in our galaxy. We have detected roughly 3,000. The rest are silent, or their beams simply never point our way. But what happens when we look at the numbers? A typical neutron star is around 20 kilometers across and contains between 1.5 and 2 times the mass of our sun. Try to hold those two facts together. All that material in an object you could walk around in an afternoon. The density works out to roughly 10 to the 17th kilograms per cubic meter. That number means nothing on its own. So here is what it means in practice. 1 cubic centimeter, about the size of a sugar cube, would weigh something like 100 million tons. A teaspoon of the deeper material would weigh 1 billion tons or more. This is the same density as the nucleus of an atom. And that is exactly what a neutron star is. Ordinary matter is almost entirely empty space, with a tiny, dense nucleus surrounded by electrons at enormous relative distances. If an atom were the size of a stadium, the nucleus would be a grain of rice at the center. A neutron star is what you get when all of that empty space is removed. It is, in a real sense, a single atomic nucleus with the mass of a star. The entire object obeys nuclear physics rather than chemistry. There are no atoms in it, no molecules, no elements in the ordinary sense. Every particle in your body could, in principle, be compressed this way. The whole of humanity, all 8 billion of us, would fit comfortably inside a cube smaller than a sugar cube. And yet, there's more to this story, because that mass in that space produces gravity unlike anything else with a surface. Surface gravity on a neutron star is roughly 200 billion times stronger than on Earth. Consider what that does to a fall. Drop an object from 1 meter above the surface. On Earth, it takes about half a second and lands gently. There, it would cross that meter in a few microseconds and strike the ground at something like 2,000 kilometers per second. Nothing survives that. Any object falling onto a neutron star is not crushed so much as instantly converted into a flash of energy. The escape velocity is around half the speed of light. To leave the surface, you would need to be traveling at 150,000 kilometers per second at the moment you left. This is also why the surface is so extraordinarily smooth. Gravity that strong will not tolerate irregularity. Any bump is pulled down relentlessly, and the crust, though incredibly rigid, cannot support height. The tallest mountains on a neutron star are thought to be measured in millimeters, possibly less. Across an entire object 20 kilometers wide, the surface may vary by no more than the thickness of a coin. It is the smoothest object in the universe, polished by a gravity to a tolerance no manufacturing process could approach. Now, let's go deeper into what one would actually look like. A neutron star is born unimaginably hot. The moment it forms, its interior temperature is somewhere around 1 trillion degrees. It does not stay that way for long, and the reason is neutrinos again. In those first seconds, the star sheds heat by producing neutrinos that stream straight out, carrying energy away far faster than light ever could from an ordinary star. Within minutes, it has cooled by a factor of 1,000. Within a century or so, the surface has settled to around 1,000,000 degrees. That is still extraordinarily hot. Our sun's surface is about 5,500 degrees. So a young neutron star radiates most of its energy not as visible light, but as X-rays, which is how the majority of them are found. If you could see one directly, it would be a fierce blue-white, far hotter in color than any ordinary star. But it would also be almost impossibly faint, because it is tiny. Brightness depends on surface area as well as temperature, and there is very little surface here. The nearest one we know of sits roughly 400 light-years away, and although it is a strong X-ray source, in visible light, it is far too dim for any but the largest telescopes. They cool slowly from there. Over millions of years, the surface fades through hundreds of thousands of degrees, and the X-ray glow weakens until the object becomes essentially undetectable. Most of the neutron stars in our galaxy are old, cold, and completely dark. They are still out there. We simply have no way to see them. The journey continues to the spin. Neutron stars rotate, and some of them rotate at speeds that sound like a mistake. The reason is a principle you have seen demonstrated by every figure skater. Angular momentum is conserved. Pull your arms in while spinning, and you speed up because the same rotation is now concentrated in a smaller radius. The original star rotated slowly. Our sun takes about a month to turn once, and massive stars are similar. Then the core collapses from the size of Earth to the size of a city. The radius shrinks by a factor of tens of thousands, and the rotation rate increases enormously to compensate. A star turning once a month becomes an object turning several times a second the moment it forms. The fastest one we have found completes 716 rotations every second. Its equator is moving at roughly a quarter of the speed of light. Picture that for a moment, astronaut. An object heavier than the sun, spinning so fast that if you could see it, it would be a blur, and yet so precisely balanced that its rotation is one of the most stable phenomena known. Magnetic fields concentrate in the same way. The star's original field is squeezed into a tiny fraction of its former volume, and its strength multiplies by a factor of billions. A collapse that takes 1 second produces an object that spins like a drill and carries a magnetic field beyond anything we can make. Now, let's go deeper into what that spin lets us do. A neutron star's magnetic poles are usually tilted relative to its rotation axis, just as Earth's magnetic pole does not sit exactly at the geographic pole. Charged particles are funneled along the field lines and accelerated to enormous speeds near the poles, producing narrow beams of radiation streaming out from each magnetic pole. As the star rotates, those beams sweep around like a lighthouse. If one happens to cross our line of sight, exactly one rotation later, then another. We call these pulsars. So much. Some of the fastest ones keep time with a precision that rivals the best atomic clocks on Earth. Over years, Certain pulsars have been shown to be stable to within a few billionths of a second. That accuracy turns them into instruments. Because the timing is so reliable, any tiny deviation carries information. If a pulsar orbits a companion, the pulses arrive slightly early on one side of the orbit and slightly late on the other. And from that pattern, we can weigh both objects with extraordinary precision. The pulses also slow down very gradually. A pulsar radiates energy, and that energy comes out of its rotation. Over millions of years, it winds down until eventually the beams weaken and it goes quiet. There is a strange rejuvenation, though. If an old, slow pulsar has a companion star, it can pull material from it. The infalling matter delivers angular momentum, and the dead pulsar spins back up to hundreds of rotations per second. Astronomers call these recycled pulsars. Old objects spun back to life by a neighbor. But what happens when the clock stumbles? Occasionally, a pulsar does something it should not. Its rotation, which had been slowing with perfect regularity for years, suddenly speeds up. The change is tiny, a fraction of a millionth of the rotation period. But it is abrupt, and it should not happen at all. Nothing is adding energy from outside. Astronomers call these events glitches, and they are our best window into the interior. The explanation involves two separate things rotating at different rates inside the same star. The crust is solid, and it is slowing down steadily as the pulsar radiates. But beneath it, much of the interior is a superfluid, a state of matter with no viscosity whatsoever, which flows without any friction at all. A superfluid cannot slow down the way ordinary material does. Instead, its rotation is carried in tiny discrete vortices, and those vortices become pinned in place against the crust above, so the crust gradually slows while the superfluid keeps spinning at its original rate. The mismatch builds, and the stress accumulates until suddenly a huge number of vortices unpin at once and transfer their angular momentum to the crust. The crust jumps forward. We see a glitch. There may also be starquakes. The crust is under enormous stress from the changing rotation, and when it fractures and resettles, the star's shape shifts by perhaps a fraction of a millimeter. That is enough to alter the spin measurably. A crack a fraction of a hair wide, detected across thousands of light years by counting pulses. And yet, there's more to this story, because that timing precision has been turned into an instrument the size of the galaxy. The idea is elegant. A gravitational wave passing through our region of space stretches and compresses the distance between us and everything else. If a wave passes between us and a pulsar, the pulses arrive very slightly early or very slightly late. The effect is tiny, billionths of a second, and easily confused with ordinary noise in any single pulsar. So astronomers monitor dozens of them at once, spread across the sky, and look for correlated deviations. A genuine gravitational wave produces a specific signature. Pulsars close together on the sky should shift in the same direction, and pulsars on opposite sides should shift in a particular opposite pattern. That correlation cannot be faked by clock errors or local noise. Several teams around the world have been timing pulsars this way for more than 15 years. In 2023, they announced evidence of exactly the expected pattern. What they appear to be detecting is a background hum of gravitational waves at extremely low frequencies. Waves with periods measured in years, produced by pairs of supermassive black holes slowly orbiting each other in the centers of merging galaxies across the universe. Ground-based detectors catch brief chirps from individual events lasting seconds. This is something entirely different. A continuous low murmur from the whole cosmos, detected by watching dead stars keep time. We built a detector out of the galaxy itself, using objects that formed long before we existed. There is one more use we found for them, and it is oddly touching. When the first spacecraft were sent on trajectories that would carry them out of the solar system, they were given plaques intended for anyone who might one day find them. The designers needed a way to say where the craft came from, without language, and without assuming any shared units of measurement. They used pulsars. Each plaque carries a diagram of lines radiating from a central point. Every line points toward a specific pulsar, and its length indicates the distance. Written along each line in simple binary is that pulsar's rotation period. Because every pulsar has its own distinctive rate, and because those rates slow in a predictable way, the diagram does two things at once. It locates the sun by triangulation, and it records when the craft departed, since anyone finding it could compare the listed periods against the slower present-day values. A map and a timestamp, written in the ticking of dead stars. And yet, there's more to this story, so let us go inside. The outermost layer is an atmosphere. It is made of plasma. It is compressed by that ferocious gravity into a shell perhaps 1 centimeter thick, and it is where most of the light we detect is produced. Below it lies the crust, and it is the strangest solid in existence. The outer crust is a lattice of atomic nuclei, mostly iron, arranged in a crystal structure and packed unimaginably tightly, with a sea of free electrons flowing between them. It is a crystal, and it is rigid, and it is about 10 billion times stronger than steel. Go deeper, and the pressure rises until something remarkable occurs. Neutrons begin leaking out of the nuclei entirely, a transition physicists call neutron drip. Below that point, the nuclei are sitting in a bath of free neutrons. And deeper still, the nuclei stop being spheres. At those pressures, the competition between nuclear attraction and electrical repulsion reshapes matter into extended structures. Simulations show nuclei merging into long rods, then into flat sheets, then into sheets with holes, then into bubbles. Physicists looked at these shapes and named them after pasta. There are gnocchi, spaghetti, and lasagna phases, and the names are entirely official. Calculations suggest nuclear pasta may be the strongest material in the universe, roughly 10 billion times harder to break than steel. If you wanted to build something indestructible, this would be the substance, and there is no possible way to obtain it. The journey continues deeper still. Below the pasta layers, the structure dissolves entirely, and we reach the outer core. Here, matter is a fluid of neutrons, with a small fraction of protons and electrons mixed in. And it is not an ordinary fluid. The neutrons form a superfluid. They flow with precisely zero viscosity, which means that once set in motion, they never slow down. Currents inside a neutron star established at its birth may still be circulating unchanged. The protons do something equally strange. They become a superconductor, carrying electrical current with no resistance whatsoever. This is thought to be how the star's colossal magnetic field is sustained without decaying. These are quantum behaviors we normally only produce in laboratories at temperatures within a whisker of absolute zero. Inside a neutron star, they occur at hundreds of millions of degrees because the density is so extreme that quantum effects dominate anyway. The inner core is where honesty is required. We do not know what is there. The pressure exceeds anything that can be reproduced or calculated with confidence. Several possibilities are taken seriously. It may simply be denser neutron fluid. It may contain exotic heavy particles that are unstable everywhere else, or the neutrons themselves may break down, releasing the quarks inside them into a free quark fluid that exists nowhere else in the universe. We have no way to look. The center of a neutron star is one of the few places in nature where our understanding of matter genuinely runs out. Now, let's go deeper into the magnetic ones. A typical neutron star has a magnetic field around 1 trillion times stronger than Earth's. That is already beyond anything achievable in a laboratory. A small fraction of them are far worse. These are magnetars, and their fields reach 1,000 times higher still, something like 1 quadrillion times Earth's magnetic field. They are the strongest magnets known to exist. At that intensity, magnetism stops being a force that pushes things around and starts altering the structure of matter itself. Atoms placed in such a field are deformed. The electron orbitals are squeezed sideways into narrow needles aligned with the field, and chemistry as we know it simply ceases to function. Molecules cannot hold their shape. The effects extend a long way. Bring a magnetar to within 1,000 kilometers of a person, and the iron in their blood and the structure of every molecule in their body would be disrupted long before they arrived. Even from halfway to the moon, a magnetar would wipe the magnetic strip on a credit card. The field is also unstable. It is wound up inside the star and under enormous stress, and occasionally it rearranges violently, cracking the crust and releasing an enormous burst of energy. These bursts are the most energetic events we know of, short of a supernova or a merger, and one of them, in 2004, produced a demonstration that is difficult to believe. But what happens when one of them lets go? On a December day in 2004, instruments across the solar system registered a sudden surge of gamma rays. The source was a magnetar roughly 50,000 light-years away on the far side of our galaxy. In about 0.2 of a second, it released more energy than our sun produces in 250,000 years. That energy crossed 50,000 light-years of space, arrived at Earth, and measurably disturbed the upper atmosphere. Our ionosphere was compressed in daylight by a star half a galaxy away. It saturated the detectors on nearly every spacecraft that saw it. Several instruments could not record the peak because it exceeded what they were built to measure. It remains the brightest event of its kind ever detected from beyond our solar system. And here is the sobering part. Had it occurred within about 10 light-years of Earth, it would have caused serious damage to our ozone layer. Fortunately, magnetars are rare. Only a few dozen have been identified. They remain highly active for perhaps 10,000 years before their fields decay, and none are anywhere near us. But it is worth appreciating what happened. A crack formed in the crust of an object 20 kilometers across on the other side of the galaxy, and the atmosphere above your head noticed. And yet, there's more to this story, because relativity behaves strangely down there. Gravity that's strong distorts both space and time in ways that are directly measurable. Time on the surface of a neutron star runs noticeably slower than time far away. The effect is around 20 to 30%. Someone standing there, if standing were survivable, would age 3 years, while 4 passed for a distant observer. And light does not travel in straight lines near the surface. It curves. The consequence is genuinely disorienting. Light leaving the far side of the star can bend around the edge and reach you anyway, which means you can see more than half of a neutron star at once. Standing above one, the horizon does not fall away as it does on Earth. It curls up toward you. You would see the far side of the object appearing around its own edges, distorted and stretched, as though the surface were wrapped over the sphere. If a hot spot rotated around to the back, it would not vanish. It would remain faintly visible, smeared around the rim. This is not a curiosity. It is a measurement tool. A recent instrument on the space station has been timing the arrival of X-rays from hot spots on rotating neutron stars. And because the amount of bending depends on the ratio of mass to radius, the shape of the pulse reveals the size of the star. We have measured objects 20 kilometers wide, thousands of light years away, by watching how their gravity bends their own light. The journey continues, to 2 of them meeting. Some neutron stars exist in pairs, orbiting each other, and a pair like that cannot last forever. As they orbit, they radiate energy as gravitational waves, ripples in the fabric of space itself. That radiation carries energy away, so the orbit slowly tightens. The process was confirmed decades ago by tracking a binary pulsar for years and watching its orbit shrink at precisely the rate predicted. It was the first strong evidence that gravitational waves exist at all. Over hundreds of millions of years, the spiral tightens. In the final minutes, the 2 stars whip around each other thousands of times, closing fast, and then they merge. In August of 2017, we caught one. Detectors on Earth registered a gravitational wave signal lasting about 100 seconds, rising in frequency as the 2 objects spiraled together. Just under 2 seconds after it ended, a satellite recorded a short burst of gamma rays from the same region of sky. Within hours, telescopes worldwide had found the source in a galaxy about 130 million light-years away. Over the following days, they watched the glowing debris expand, cool, and shift from blue toward deep red. It was the first time an event had been observed with both gravitational waves and light, and it settled several long-standing questions at once. Now, let's go deeper. into what that glow was made of. The fading light from that collision, and it answered a question that had been open for decades. Elements come from. Elements up to iron are produced inside stars by ordinary fusion. Beyond iron, fusion no longer releases energy, so a different process is required. The heaviest elements must be built by rapidly adding neutrons to existing nuclei, faster than those nuclei can decay. That requires an environment absolutely flooded with free neutrons. Supernovae, say, were long assumed to be responsible, but calculations struggled to produce enough. A neutron-star merger is, by definition, the most neutron-rich event possible. When two of them collide, a small fraction of their material is flung outward. That material is essentially pure neutrons, suddenly released from the pressure that held it together, and it immediately begins forming the heaviest elements in the periodic table. The 2017 event produced an estimated several Earth masses of gold and platinum in a matter of seconds, which leads somewhere personal. The gold in a wedding ring was not made on Earth, and it was not made in the sun. Almost all of it was forged in a collision between two dead stars, somewhere in this galaxy, billions of years before the Earth existed. It drifted through space, mixed into the cloud that formed our solar system, and eventually ended up in the ground. Every piece of gold jewelry is a fragment of an event like the one we just described. But what happens if a neutron star gets too heavy? There is an upper limit, and crossing it changes everything. Neutron degeneracy pressure is strong, but it is not infinite. Pile on enough mass and it fails, exactly as electron pressure failed in the original iron core. The limit appears to sit somewhere around 2.2 to 2.3 times the mass of the Sun, though the exact value depends on the behavior of matter at densities we cannot test. Below that line, you have a neutron star with a surface. Above it, nothing can hold, and the collapse continues all the way down to a black hole. This is why measuring neutron star masses matters so much. Every heavy one discovered raises the floor of the possible answer and rules out theories that predicted a softer limit. Objects of around 2 solar masses have now been measured convincingly. There is also an awkward gap. For years, astronomers found almost nothing between about 2 and 5 solar masses, heavier than any confirmed neutron star, lighter than any confirmed black hole. Gravitational wave detectors have since found a few objects in that range, and in some cases, nobody can say with confidence which kind they are. The merger we watched in 2017 may itself have produced one briefly. The combined mass appears to have been right at the boundary. It may have survived as an unusually heavy neutron star for a fraction of a second before giving up and collapsing. The line between having a surface and having none is thinner than anyone expected. Take a quiet moment to reflect on what this means, astronaut. There is something worth sitting with in all of this, and it is not the extremity of the numbers. Everything we have described tonight is the remains of something that ended. A neutron star is not a beginning. It is what is left after a star exhausted its fuel, failed, and was blown apart. It is wreckage. And yet that wreckage is where the universe does some of its most remarkable work. It builds the strongest material in existence. It maintains clocks more reliable than almost anything humans have engineered. It preserves currents that have flowed without resistance since the day it formed. And when two of them finally fall into each other, they manufacture the heaviest elements the periodic table contains and scatter them outward to be built into planets. Nothing about this is careful, and nothing about it is wasted. The universe does not appear to distinguish between destruction and creation. They are the same process, viewed at different moments. There is a quiet thought in that. The gold in the ring on someone's hand, the platinum in your body, all of it was made by things dying badly could survive. We are assembled in part from the debris of catastrophes, and the result is calm enough to lie in a warm room and wonder about it. We drift away now, leaving that small bright sphere behind, 20 kilometers wide, turning hundreds of times a second, glowing faintly with heat it has been losing for 1,000,000 years. It will keep going. Its rotation will slow by a few billionths of a second each day. Its magnetic field will weaken over millions of years. Eventually the beams will fade, and it will become a cold, dark, perfectly smooth object, still spinning, still carrying its superfluid currents, drifting quietly through the galaxy for longer than the universe has so far existed. There is no drama left in it. Everything violent about it happened long ago in a single second. Close your eyes now. Somewhere out there, something impossibly dense is turning steadily in the dark, keeping better time than any clock ever built. And it will still be keeping it in the morning. Mission complete, astronaut. The stars will wait for you. Good night.